All right. Last unit of organic chemistry. Then we have our exam next week, and then we start the last 3 units, biochemistry. So we've started with just our basic organic structures, right? Carbon, our hydrocarbons. We involved some oxygen on Tuesday. Now we're going to involve nitrogen into this. And one thing to keep in mind about this unit is towards the end of the unit, when we involve nitrogen, is that we bring in the idea of ammonia, right? And ammonia is a base, right? Ammonia is a base. Water can act as an acid and donates hydrogen, donates hydrogen, accepts hydrogen, and we get ammonium and water's conjugate base. So just kind of keep this idea when we start introducing these, is that these structures that involve nitrogen are going to be considered bases, right? So here's a structure, organic structure, methane. So this is methane, right? This isn't acidic, this isn't basic, but if I do this, now it becomes a basic structure, right? So now this is a base, simply because I involved nitrogen here in that manner. So we'll just kind of keep that in the back of our minds when we're dealing with these, because we're going to have to go through some reactions that we call acid and base hydrolysis, and it involves these nitrogen-based organic products. So one reaction that we talked about, oxidation reaction, right? So let's kind of recall oxidation reaction. So when we're considering primary alcohols, we consider a primary alcohol. Let's draw one here. And let's also do it in a condensed structural formula. All right. So primary alcohol, simply because this carbon here, this is the carbon that contains the alcohol group. This carbon has only one other carbon-to-carbon bond, right? So primary alcohol. Does anybody recall what happens? I'm going to use an actual oxidizing agent. We're going to oxidize it. So you might see some catalyst here, especially on the exam. You might see a catalyst, or you might see something like this. Either way, we're going to consider this to be a catalyst. We're going to ignore it. We know it's going to get oxidized, but does somebody recall what we're going to get when we oxidize a primary alcohol? Gabrielle? An aldehyde, right? So we're going to get some aldehyde structure. I'm going to underline this al here real quick. So we're going to lose one of these hydrogens here. That's what happens when we oxidize. We're going to lose one hydrogen, and we're going to create our carbonyl. So we're going to get this structure here. Here's the oxygen. I've removed one of the hydrogens. I'm going to now form that carbonyl. And we get some aldehyde. And let's do this in condensed structural formula. And again, we see our carbonyl here, right? And we also understand, let's see, Gabriella, let's continue. Do we know what we get when we oxidize it a second time? Carboxylic acid. Yes, you're on it. Good. So we're going to get a carboxylic acid. So this is what we consider a carboxylic acid. So we're going to oxidize it, and that means that this hydrogen here, this last hydrogen on this carbon is going to be removed, and we're going to replace it with this hydroxide group. So we're going to get CH3, CH2, CH2. And we get this carboxylic acid. Right? So let's just start naming these carboxylic acids. And first, I'm gonna write a new reaction on the board. Carboxylic, or maybe I'll just use this part underneath here. Carboxylic acid. I'm going to write something down. When we use IUPAC naming, right, is that we're going to, instead of just remove, I'm going to say drop. So we're going to drop the E and add oic acid. Right, we're going to drop the E, and we're going to add oic acid. So, just by looking at this structure here, and I said it in Chapter 7 that we're really just concerned not with how many hydrogens we have, but how many carbons we have. Because to find the parent name, we change the structure a little bit, change the alkane structure, and then we have to change the name. So if we're going to count this is carbon number 1, 2, 3, 4. In order to name this, I'm concerned with one thing. What's the alkane that has 4 carbons? Butane. So if I want to name this, this is where I'm going to start. I know that it comes from butane, and then we're just going to remember this rule here. We're going to drop the E, and we're going to add oic acid, and we get butanoic acid. And that's how we're going to name these using that IUPAC naming system. So now we can put a bunch of other ones up here. Let's go with line formula. I'm going to draw it on this side. Zoe, how many carbons are in this structure? 5. Perfect. 1, 2, 3, 4, 5. And on the exam, if you have to write in the number of the carbons this way, it's perfectly fine to do that on the exam. Absolutely. So here, so again, the first thing we're going to be concerned with is what's the alkane that has 5 carbons there?
Pentane.
Pentane. So here, pentane. And what are we going to change pentane into?
Benzoic acid.
Pentanoic acid. Yeah, so we don't want to drop too much. We're not dropping the A any, is that we're only dropping the E from pentane. So this is going to go away, and we're going to get pentanoic acid. Pentanoic acid. So let's draw this structure, right? And this structure is going to have some branches. And again, I'm not concerned with the branches right now. What I'm concerned with is the alkane that I'm going to turn into a carboxylic acid. Right? So nothing's going to start without that alkane. So how many carbons am I going to need for octanoic acid? 8. So let's start there. So there's 1, 2, 3, 4, 5, 6, 7, 8. And because I'm drawing it, I get to choose carbon number 1. Now I'm going to put carbon number 1 on this side. Now, if this is carbon number 1, carbon number 1 is where we have our carbonyl. Right? We're not going to do this and add the carbonyl, right? Carbon number 1, that's where we have our carbonyl. So let's draw that. So I've drawn the carbonyl, and for carboxylic acid, what is it that I'm going to add right here? An OH, right? Because we're memorizing these, and we know that carboxylic acids look like this, right? Not an aldehyde, okay? Carboxylic acid, and we need that OH there, so we're going to add OH. So now we have octanoic acid, so this is taken care of. We'll just number these here, 3, 4, 5, 6, 7, 8. Carbon number 4, we get a methyl group, and carbon number 3, we're going to get some isopropyl here. Let's do this. Let's stay with this structure here. I'm going to redraw it. I'm going to make one change to it. And we're going to name this structure. Okay? So on carbon number 3, we still have this isopropyl. On carbon number 4, we still have that methyl group. But how about I've now put in a double bond, which means it's no longer, we have, and just as a reminder here, right, single bonds, this is an alkane, double bonds, right, this would be an alkene, because double bonds, and then if we had a triple bond, then that would be an alkyne, but this alkene instead of an alkane. So if we had to name this structure down here, I'll get this started. Still 3-isopropyl. We still have 4-methyl. Brian, where does carbon number, or where does the double bond begin in this structure? On carbon number 2. And would it still be octanoic acid, or would we change that, Brian? Change it to what? Alkene. So it's an alkene. So instead of octanoic acid, we would call it say that again? Octene oic acid. So this would be, right, this is now 3-isopropyl 4-methyl octanoic acid, and this would be 3-isopropyl 4-methyl 2-octene oic acid, right? It won't get more, I don't think I even have anything this complex on that. You might see something like that on the homework, but I'm almost certain there's nothing like that on the exam. But let's name one more. Okay, so let's go then. Kayla Bowden, help me out here. All right, so how many carbons are in how many carbons are in the parent chain?
6.
6, right. So we have 6 carbons, and what's the alkane that has 6 carbons? Hexane, perfect. So good. You didn't even have to look. I'm so proud of you. All right, so it is 6-hexane, but we're going to turn hexane into what? We're gonna drop this E, and we're gonna add hexanoic acid. So great. So we now have hexanoic acid. All right. Do we know this here. What is this? It's not isopropyl, because isopropyl would look like this. So this is 2, what's the name of these here? Methyl, right? So this is methyl, and they're both on carbon number 2. So because they're the same, what prefix could we use for that? Dimethyl, perfect. Dimethyl, and they're both on carbon number 2, so we're going to put 2, 2. If I have 2 branches, I need 2 numbers, right? So here again, this is on carbon number 3, carbon number 4. They're both identical, so what would we name that? 3,4-dichloro. And which one would come first? Dichloro. So we're going to start with that. We're going to say this is going to be 3,4-dichloro, 2,2-dimethyl hexanoic acid. Perfect, perfect. All right. Let's talk about another carboxylic acid. This is one that we have to memorize. We know this structure here. Right? For the exam, I would want to know the formula for this, right? If I'm taking an exam in my class, I would definitely want to know what the formula is for this. Wink, wink, right? I'd want to know what the formula is for that. So this is C6H6, and this is benzene. If I happen to put a carboxylic acid onto it, again, we're going to drop the E. Or no, actually this is sorry, scratch that. Special name here. It's not benzenoic acid. Let me correct that. It is benzoic acid. Benzoic acid. So this is one that we need to memorize, right? We need to memorize that structure. And this is the name we're going to use. So again, it's not some 2,6,3 hexene, triene, this is benzoic acid. We just memorize it. Benzene, benzoic acid, aniline, right? Toluene, we just memorize all those. Phenyl. But let's go ahead and put, I'm going to move, right? There's some confusion, and students always kind of go to here and say this is carbon number 1 because it's at the top, and that's not the case here. I'm going to move this carbonyl. Let's put it here. Right? So we recognize carbonyl, my hydroxide. This is a benzoic acid, right? Even though it doesn't look like the regular way, this is still benzoic acid. And let's put fluorine here. Let's put chlorine here. Let's put bromine here. Okay. So I have 3 different halogens here, right? Remember how to name our halogens: chloro, fluoro, iodo, bromo. This is carbon number 1 here. Wherever the functional group is at, carbon number 1. Are we going to count clockwise or counterclockwise? Sophia? Counterclockwise. So we're going to count this way. Yeah, so we're going to count this way. All right, so here, this is going to be 2, 3, 4. And this one, I don't think we'll make a list. We're just going to kind of write this one as we see it here. So bromo, chloro, or fluoro first? Bromo, because we're using alphabetical order. So we're going to put 4 bromo. And what would come next? Chloro, so we'll put 3 chloro. And then lastly, we would put fluoro, carbon number 2. And remember, U before R, it's not fluoro, right? It's not flower O, fluoro. And this is benzoic acid. Benzoic acid. or I'm sorry, Adam, not Andrew, Adam. Adam, how many carbons are in the structure?
Two.
Two. So this is going to come from ethane, but we're going to rename it. And what is the name of this here?
Ethanoic.
Ethanoic acid. Perfect. This is ethanoic acid. And let me draw one more next to it. Let's go with this is going to be H. This is going to be OH. And I know that it looks like an aldehyde because I see that H there, but this is not an aldehyde. We're going to go with the OH here, okay? And this is carboxylic acid. But this only has one carbon. All right, so Montalene, what would we call this? This comes from methane because there's just one carbon here. But we're going to change this. We're going to drop the E. We're going to add oic acid. So how would we rename this?
Methanoic acid.
Perfect. Methanoic acid. All right. Now, this is what we call IUPAC name. I'm going to get another marker. This one's starting to fizzle out. Oh, not much better. We also need to learn the common names for these. Okay? And just as a reminder, if we're using common, one carbon, we use the prefix form. And if it's two carbons, we use the prefix acete. So form and acete. So these common forms here are just going to take this here, ic acid. So when we started the lecture, right, I gave you a rule up here, and I also put IUPAC. IUPAC naming, we're going to add oic acid to the IUPAC name. It's oic acid. For common naming, it's not oic. For common names, it's just ic acid. And we're going to go with these prefixes here. Okay? We're going to use these prefixes. This one is one carbon, this one is two carbon, and then we're just going to add to the end of it ic acid. All right? So Anna, how many carbons are in this structure? One. So which prefix would we use? Form. And how are we going to end it? Ic acid. So what is the name of this here? Formic acid. So now, how many carbons are in here? Two. There's one right here. There's another right here. Name this for me. Just how we did here, right? We used form, and then we added ic acid, formic acid. This is acete, so what would we call that? Acetic acid. So this is acetic acid. So now we have common and IUPAC names for carboxylic acids. Okay? Acetic acid. So we do have to know those as well. So now we know our benzoic acid. We know IUPAC naming here. Oh, let's take a look at a reaction using carboxylic acids. Carboxylic acids strong acid or weak acid? This is an easy. This is a gimme. Strong acid or weak acid. It is a carboxylic acid. We know that it's an acid because it's in the name, benzoic acid. But is this a strong acid or weak acid? Is it one of the 6 strong acids that you memorized? No. So then is it a strong acid or weak acid? It's a weak acid because it's not one of the 6 that we memorized. You know, way back when we were in chapter 6, right? Okay. So carboxylic acids, they're weak acids. But nonetheless, they are acids. So let's take this particular acid here. We're going to take some acetic acid, and let me draw this in a condensed structural formula first. So CH3, C, and this is acetic acid. Acetic acid. Does anybody recall how we ionize acids? What is it that we add to ionize an acid? We put it in what? Rhymes with otter. Water, perfect, yeah. So this is, we just simply add it to some water. All right? So acetic acid, we're going to put it in some water. It's going to ionize. If this is my acid, then this must act as my base. It's not a base, but it's going to act as our base. Hydrogen proton donor, hydrogen proton acceptor. So this is going to take this oxygen here, I'm sorry, this hydrogen here, and there, it's going to donate that hydrogen. We get this negative charge, plus we get some hydronium here. This is my acid, this is my conjugate base. If this is acting as my base, this is our conjugate acid here. Right? But we can ionize any carboxylic acid. Or just put it in water and we ionize it. And it's always just removing this hydrogen. We always just remove this hydrogen. This structure here, this is what we call a carboxyl. It's not a carboxylic acid. Why isn't this a carboxylic acid? What is it missing? The hydrogen. It's kind of like a carboxylic acid, but it's missing the hydrogen, that we call this a carboxylate ion. This is a carboxylate ion. Now, can someone give me the name of this? What is this here? Everybody should know this. We don't know this. You know this. You just don't know that you know this, right? But you all know this. I'm gonna rewrite this for everybody, and then you're gonna be like, oh, all right, I got it. Ready? How many carbons are here? And how many hydrogens are here? And how many oxygens? What is the name of this? What is it? It's your polyatomic? Acetate. This here is acetate. Acetate. That this is acetate here. So we do know what the structure is. So when we ionize carboxylic acids, we drop this ic acid. Right? We drop ic acid and we add ATE. We drop ic acid and we add ATE. So let's take formic acid. We're just going to stick it in some water. And we're going to ionize it. We're going to just, all we do is we simply rewrite it like it was a carboxylic acid. We just simply remove the H here. This is our carboxylate, plus we're going to get H3O plus. This is formic acid. So when we convert this into our ionize it and it becomes our carboxylate ion, what is it that we're going to remove here? What part of this name is going to go away? The ic acid. We're going to remove ic acid, and what are we going to add to it? 8. So acetic acid, acetate, formic acid, we're going to get what, Hannah? Formic. This is now form 8. Right. We're going to get into some structures in just a little bit called esters. And it's going to look similar to this. And we're going to have to remember these rules when we're dealing with esters. And when we see something like this, we have our carbonyl, because we have different structures that have carbonyls. Is that here we have this structure, then we also have this structure here where we're going to have some, carbons there. And then we also now have, this structure here where we're going to have this here, this. All right, so we have to differentiate all of these here. And then there's going to be a third one that we're also going to add later today that contains nitrogen. And we have to know how to identify them, right? Carbonyl with a hydrogen, aldehyde, right? This is an aldehyde. Aldehyde. This is how I know my aldehydes. Carbonyl, aldehyde, I'm specifically looking for a hydrogen on that carbonyl, right? My aldehydes have a hydrogen and my ketone don't. That's just how I remember it. It's a goofy sentence, but my aldehydes have a hydrogen and my ketone don't. That this is a ketone. My carboxylic acid, I just have to memorize that. Carboxylic acid. Without the hydrogen, kind of looks like this. This must be my carboxyl 8 ion, right? This one is an amide, but we'll talk about that later. Actually, let me introduce the idea now, and I'm going to write it a special way here. This is what we call I put that in red specifically because, again, this is just simply how I memorize. You can memorize it different ways, but how I memorize what an amide looks like is that, one, I think of ammonia, and ammonia has nitrogen. An amide, ammonia, there's a nitrogen here. But I'm also looking for this D here that contains this double bond. Because there's another functional group that we call an amine. And I don't want to mix this up with an amine, right? Amine. I don't want to mix it up with an amine. That an amide specifically, I'm looking for this double bond. If it doesn't have this double bond in nitrogen, then I know it's my amine, right? But amide, D, got to have that double bond. But let's get back to here. We got a little off track, but we need to know these structures. So we're still talking about these carboxylates and how we name them. So we've done acetic acid, acetate, formic acid, form 8. So regardless if it's common, regardless if it's IUPAC, as far as ionizing a carboxylic acid, and I'm going to put carboxylate here. Let me put carboxylate. This is just kind of our rule for carboxylate ions, is that we're going to drop the ic acid and we're going to add ATE. All right. Doesn't matter if it's common IUPAC. This is our rule for carboxylate ions. And let me draw another carboxylic acid. So first I'll draw the carboxylic acid, and then I'm going to draw next to it our carboxylate ion. So carboxylic acid, carboxylate. Kaylin, what's the name of this carboxylic acid? First, how many carbons are here? 4. So do you know the alkane name for 4? Butane. Perfect. So now, as far as the carboxylic acid goes, right, we're going to drop the E. We're going to add oic acid. So what's the name of the carboxylic acid? Butanoic acid. Perfect. Butanoic acid. Now, let's stay with this, all right? Let's stay with this, Kaylin. Butanoic acid. So the rule for our carboxylate ions is we're going to drop the ic acid, right? We're going to remove ic acid. Notice that we're not removing oic acid. We're just removing ic acid. And then we're going to add ATE. So then this becomes butanoate, butanoate. Right? It's not butanate, because we're not removing oic acid, we're just removing ic acid from that. Right? It's the same thing we did here. Right? Remove the ic acid, acetic acid, acetate, formic acid, formate, butanoic acid, butanoate, propanoic acid, propanoate, hexanoate, heptanoate, octanoate. Right? Because we need to recognize these carboxylate ions. So let's see. Let's do a couple more carboxylate ions here. All right. Anybody brave? Want to name this here? First, yeah. Just go ahead and just name this. It comes from pentane, correct? It comes from pentane. But here, pentano what? Pentanoate, perfect, yes. This is pentanoate, right? And we're going to put this, because it's an ion here, we'll say it's a pentanoate ion, right? A pentanoate ion, perfect. About this one here. So this is no longer benzoic acid, right? This came from benzoic acid. I'm going to write that down. I'm just going to write benzoic acid. Drop the ic acid. Hosue, what is the name of this carboxylate ion? Benzoate. That this is a benzoate ion. Right? Benzoate ion. Now, let's do There's one more common name I'm going to show you because it's going to come up in today's lab. Lab 9 is what we're working on today. This has an IUPAC name, and it also has a common name. This has a hydroxy on here. So there's a hydroxide group here. Pretty sure it's in today's lab. Let me double check. Pretty sure it's in today's lab. We're working on lab 9. And yes, it is. All right. This being carbon number 1, this being carbon number 2, this is a hydroxy. I'm going to name this for us. So this is 2-hydroxy benzoic acid. 2-hydroxy benzoic acid. This also has a common name. If anybody has tried to get rid of a wart, they may have used salicylic acid, right? And this is salicylic acid, so commonly known as salicylic acid, but IUPAC naming is 2-hydroxybenzoic acid. I'm only going to do the common name for this, right? Is that we could name it 2-hydroxybenzoate, and actually I'll write that down. Let me write that down. So this is 2-hydroxy benzoate. We just removed the ic acid. We had ATE, so 2-hydroxybenzoate. Formic acid, form 8. Acetic acid, acetate. Salicylic acid. Zuri, what could we name this?
Salicylic.
8. Yes, that's it. So this is salicylate. All right. So that's going to show up. That'll show up in your lab today as far as drawing the structure out. But this is the answer for that on that part of the lab. I think it's in part 1 of the lab. But really good handle. I think we've got a really good handle on these carboxylate ions. Is that what we've talked about is, let's see, are we going to be hydrolysis? I might jump ahead real quick to come back to this, or should we just wait? Let's wait. We won't jump ahead. We'll just kind of stick with what we're going here. Carboxylic acid. All right. We talked about ionizing these. Right, so we ionize them, we just put it in water, we ionize it, but acids can also be neutralized. We can neutralize a carboxylic acid instead of just ionizing it. So let's take the small one here. We'll take acetic acid. So carboxylic acid. And let's add an actual base, not water that acts like a base, but this is an actual base, right? So carboxylic acid, this is our base. And we are now going to neutralize. Neutralization of carboxylic acid. If this is my acid, this is my base. Acids donate hydrogen. That's still the same hydrogen. We're still going to donate that same hydrogen. And anytime we're neutralizing something, we're producing water. Because water is neutral. When we neutralize it, the more water we produce, the more neutral it becomes. Okay? So we're going to be making water. which means that water is going to come from here. So we're going to split this apart. We're going to get this ion here. We're going to get this ion here. We remove this, and we're going to get this ion here. So this is where our water is going to come from. So this is us making water. We're neutralized it. We're producing water. And we get our carboxylate. Right, so nothing happened. We still get acetate here. Right? Acetic acid, we still get acetate. But instead of hydronium, like we were ionizing it, we're just producing water. But we do have this to take care of now. Right? So this positively charged ion is attracted to the negative charge of acetate. So we're just going to put it right next door, and we're going to leave the charges there. Right? We're simply going to leave the charges there. Now, we do have to name this. We do have to name it, and let's do this. If I did, right, can someone name this for me? Sodium chloride. This is sodium chloride. What we did is we named the metal, we named the cation, then we named the anion. Right? We named the cation, then we named the anion. And we still do the same thing here. Right? What's the name of the cation? This is potassium. Potassium, and what's the name of the cation? So this is potassium acetate. Oh, I spelled that horribly. I don't know how you guys deal with my writing. I know it's sloppy. Man, wow. I'm glad I'm not writing my own notes. All right, there we go. So we get potassium acetate. So here we have benzoate. This is our carboxylate ion. Benzoate. But this time, let's put all right. I recognize that this is not an aldehyde. It's not a carboxylic acid. It's not a ketone. I have this carbonyl with this oxygen negative charge. This is a carboxylate. You know, it is benzoate. And this is sodium. So, Azalea, how would we name this structure then? We name the metal first. What's the name of the metal? Sodium. And then we name the carboxylate. Do you remember what the name of this was? You can look at your notes. It's okay. What's the name of that structure? It came from benzoic acid, right? It came from benzoic acid, but we dropped the ic acid and we add ATE. So what is the name of this here? We drop the ic acid and we add ATE, benzoate. So this is sodium benzoate. So that becomes sodium benzoate. Right? So we're now able to neutralize these. Now, I'm going to show you one additional reaction here. How about, let's use butanoic acid, and we're going to use calcium hydroxide. So still a base, acid base. This is 1 minus, right? There's 2 of them here. So when we split this apart, we're going to get this. Right? So we're going to get this, and that's going to form 2 waters. But what's the charge on calcium, real quick? It's in group 2. So the charge on this would be, yeah, so this is 2 plus. So we're going to put that, and again, we always do this, so we go 2 plus. This cancels this charge. Does this cancel this charge? Yeah. Any ideas how we can fix that? Let's do a little bit of review. If I did this, what would the formula be to put this together? Yeah, we need 2 of these, so we put CaF2. So all we do is put a subscript here, right? So same solution for this is we can put this in parentheses here, and then just add a subscript 2, just like this here. So here, this is 1, 2, 3, 4. So it comes from butanoic acid, or butanoic acid. So let's name the structure here. What's your name? I'm sorry.
Chris.
Chris. So Chris, let's involve Chris here. Chris, what would I name? We're going to name the metal first. So what's the name of the metal? Calcium. So we've named the cation, calcium. And this comes from this comes from butanoic acid, but it's a carboxylate, so we're going to change that to butanoate. And now because it's with calcium, we don't have to put an ion anymore. So this just becomes calcium butanoate. All right, so we're good. All right, good job. So now we're going to involve the esters that I mentioned before, and I'm gonna kind of work on this half of the board here. I'm going to leave this up for a little while because I want everybody to recognize this here, right? This is butanoate. So I'm just going to kind of leave that there for a little bit. I'll try to work on this side of the board for us. Do you have any more blue markers? Green, black. All right. So we're now going to talk about esters. The basic structure of an ester is we have our carbonyl. This is bonded to some random carbon chain. And then we have an oxygen. And then we have another random chain. Right? We're going to bring back the idea of ethers that we learned the other day. I'm going to give us a simple one here. Let's go with CH2, CH3, CH3. This is an ether. So, Milex, what's the name of this ether here? So, we're first going to name, we recognize that these are branches, okay? What's the name of this branch? All of our branches are all alkyl branches. So they all end in YL. Methyl, ethyl, propyl, isopropyl, right? Those are our branches. So this has one, so it's not methane, but we would call it Methyl. Perfect. So this is methyl. 2 carbons is not ethane. We would call this ethyl. So this is ethyl. And then we would name it ether. So here we're going to put this in alphabetical order, and we would call this ethyl methyl ether. Ethyl methyl ether. So let's just kind of keep that in mind, right? Because this, here's an oxygen, and here's a branch that's coming off of the oxygen, right? This is my oxygen. Here's a branch that's coming off of this oxygen. Now, this portion here, we've been talking about this probably for the last 20, 30 minutes. What does this look like? There's no hydrogen there. There's just an oxygen. So it's not OH, it's not H, it's not an aldehyde, it's not a ketone, it is a carboxylate. That this is resembling our carboxylates that we've been working with. And we're going to use 2 different rules here to name these esters. Is one, we're going to split this in half. Right here. So we have 1/2 that looks like a carboxylate, and we know how to name our carboxylates. And the other half kind of looks like an ether, and we know how to name these branches. So it's not necessarily, we're not going to use the name ether, but we have to just kind of remember that this is just going to be some alkyl branch that we're going to put there. So let me just draw one out so we can get started. And let me divide this in half. We get a red marker here. We're going to split it right down the middle of this oxygen. And we now have 2 halves. And in order to name this, we are going to first name the branch. Right? Name the branch. And I'm going to put off the oxygen. Let me see how complex. I don't think these get too complex that we're putting branches on these, but let me just double check. Yeah, I don't believe we're putting branches on. Okay, so we're not going to put it. Okay, so we're going to say name the branch. And then second, we're going to say name the carboxylate. So it's not that we're going to name it left to right, right to left. I'm going to draw another one here. And this time I'm going to draw it this way. How about we put... I'm going to draw it over here. Don't want that. Let's go with... All right, so I have 2 different ones here. We name each one of these here. Again, we split it at the oxygen. Right. So if I'm looking at this structure, well, am I going to name the left half first or the right half first? We name the branch, and then we name the carboxylate. So we'll name this, because this side has the branch. So we're going to name this side first, and then we'll name this side. So if we look at this structure over here, right? Well, this half is my carboxylate, and this half is the branch. So we would name this first, and then we would name this half here, right? The carboxylate That's the half that contains the carbonyl. Carboxylate contains the carbonyl. So what is the name? Can somebody give me the name of this branch here? Melissa? Methyl. So this is methyl. 1, 2, 3 carbons here. What's the name of this? So we drop the E. OH. So we have methyl propanoate. That this is methyl propanoate. And this is how we name our esters, right? We name the branch, and then we use that carboxylate rule for naming those ions here. Chris, what's the name of this branch here? Propyl. So this is propyl. I'm just going to take this here, and this has here 1, 2, 3, 4 carbons in it. What would we name the carboxylate portion? So there's 4. Butanoate. Perfect. So this is propyl butanoate. And notice there's a space here. It's not one word. It's not propyl butanoate. It's that we have propyl, and then we have our butanoate. Oh, let's see. Let's name a couple more here. Those are the rules there for naming what we call esters. Let's use line formula. All right. So just to kind of help us out, give us some visual, I'm going to split this half right here. And Gabriella, which half am I going to name first? The right side, because this is our branch. And then we'll name the carboxylate portion. So how many carbons are in this branch? 1, 2, 3, 4. So what's the name of that branch? Butyl. So this is butyl. And how many carbons are in the carboxylate? So butyl, pentane what? Pentanoate, because it's going to come from pentanoic acid, right? So we have butyl pentanoate. Do one more here. Yeah, there we go. We're going to split this down the middle over here. So, what's the name of this branch? Isopropyl. Yeah, recognize that it looks like this, that this is definitely an isopropyl here, because it's bonded to carbon number 1, 2, 3, and it's bonded to carbon number 2. So this is isopropyl. And then we'll just number these carbons here, 4, 5, 6. So isopropyl what? Hexanoate. So isopropyl hexanoate. Oh, how about one more? One more that's kind of familiar. I'm going to pull one from the lab real quick. So lab 9, I am looking, because you're going to be making these equations in the lab today. But there's one here that we'll take. We're going to take... All right. So let's recognize where we're splitting this at, right? We find the oxygen here that breaks it up. We're going to just split that down the middle. We're going to name this half. We're going to name this half. And this, remember, this came from, this isn't the name of it, but it came from salicylic acid. Okay, so it came from salicylic acid. So somebody throw out the name of this branch. This is methyl, but it's not salicylic acid, it's salicylate. Salicylate. So that becomes methyl salicylate. All right, so we know how to name our esters. Let's take a look at a couple of reactions, and then we'll take a break before we get into amines. So we've done our carboxylic acids, our carboxylates. We've also named esters. All right, so we're doing really good. I'm getting a lot of really great answers. So I feel like you guys are going to do great on this next exam. All right. So this is what we call acid, or actually, let's do esterification. There's 3 reactions that we have to do. 3 reactions. Esterification. Right? This is how we make an ester. So esters, esterification, in order to make one of these, we need a carboxylic acid plus some alcohol, and we're going to get some ester. Right? Carboxylic acid plus an alcohol, and that's going to make our ester in this esterification reaction. So let's take some carboxylic acid plus, let's take an alcohol we're going to need some acid for this, and we're going to need a little bit of heat. This is a reversible reaction. So some carboxylic acid and some alcohol. And in an esterification reaction, we are going to produce water. Now, because of this oxygen here and this double bond, right, here, we're gonna, it weakens this bond here, right? It weakens this bond here. So in order to get our water, we're going to break this bond here. Right? And we're also going to remove this hydrogen here. So this and this will make water. Now, what I'm going to do next is I'm gonna rewrite this. So here, and actually here, when this leaves, this is how it leaves. OH negative, right? Hydroxide leaves. If this leaves as a negative, and it takes these additional electrons with it, and that's how it's negative, what's the charge on the carbon going to be? Positive. Is that we would have some positive charge left on it. So to help us understand, this is what I'm gonna just write that here, CH3, C, and there's no bond here. I just removed it for the water here, but I am gonna note that this is positively charged. When this leaves, it leaves as H plus. So that's how these two meet. H plus, O minus, they meet together, right? They're attracted to each other, they make water. But because this leaves as H plus, it's leaving behind those electrons. So what's the charge on the oxygen then?
Negative.
It's negative. This oxygen is negatively charged. Now, I'm just going to write this down here real quick. Would it make more sense to take this carbon and bond it to this carbon, or to take this negatively charged oxygen and bond it to this positively charged carbon? It'd make more sense to bond this. So what we need to do is we're going to spin this around. We're going to spin this around like my famous magic trick, right? We're going to spin that around. So we're just going to take the oxygen, and we're just going to write it in reverse. CH2, another CH2, and then we have CH3. It's like an O here. Let me rewrite that. CH3. But it is the same thing, but we just flipped it around here. Okay? And this is our esters. We take, again, carboxylic acid plus some alcohol. We get an ester, plus we get a little bit of water in that esterification reaction. And it doesn't matter what carboxylic acid it is, what alcohol it is. If we put in a little bit of acid, add a little heat to it, it will make an ester. So we just need to just kind of memorize that reaction there. Carboxylic acid plus alcohol, and we're going to get some ester. Let's use line formula here. Oh, and you know what? We should probably name this real quick, just to maybe get some practice here, right? Is that this is where we divide it from. This is going to be propyl. This is, you know what? And I want the common name for that. So here, if this is propyl, what's the common name for this carboxylate with two carbons? Acetate. So this is acetate. We name the branch, then we name the carboxylate, and this becomes propyl space acetate, propyl acetate. Here's our carboxylic acid. This time we're going to add isopropyl, right? Isopropyl alcohol. Isopropyl alcohol, right? That's our common name for this. IUPAC name here. This is carbon 1, 2, 3. Propane, propanol, 2-propanol, but commonly known as isopropyl alcohol. All right. We're going to break this bond here. We're going to remove this hydrogen here. Let's use sulfuric acid for this one, because we're going to be using sulfuric acid today. The first thing we're going to get is we're just going to get some water. And the water comes from removing this and removing this. And the next step, I've always just done it the same way, is I redraw the carboxylic acid, but I draw it without the OH, because that part was removed in the reaction just to make some water. We're going to spin this around. I'm going to bond my oxygen to that. And here we have our ester. So here, this is isopropyl butanoate. Isopropyl butanoate. All Now let's talk about two more reactions. This is where we're going to do acid hydrolysis. So we're going to do acid hydrolysis of an ester. 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 This reaction is reversible. So in order to make an acid, we do esterification. Take some carboxylic acid, add some alcohol, and make an ester and water. And when we hydrolyze it, this word here, lysis, right, means to break apart. We're going to break it apart with some water. We're going to break this apart. If we reverse the reaction where it says hydrolysis, acid hydrolysis of an ester, we're going to use acid, we're going to use water to break this apart, and we're going to get alcohol and some carboxylic acid. So this reaction is reversible. So if we were to take the same ester plus we're going to add water to it. We're going to need some acid for this and a little bit of heat. Acid hydrolysis of an ester is the same bond that we made in esterification, is the same one that we're going to break apart. The water will also get split apart. So let's just break those two apart. We're going to get this, plus we're going to get this. We have two places where we can put the hydrogen. Could put it here, could put it here. Now, if we reverse the reaction, right, we're not going to make an aldehyde, right? If we reverse the reaction, we're going to alcohol carboxylic acid. So we're going to get an alcohol, and we're going to get a carboxylic acid. So this is acid hydrolysis. If I want to make an ester, esterification is the reverse of this. Carboxylic acid plus alcohol, we're going to get an ester and some water. But acid hydrolysis, we're going to take our ester, add water, break that bond with some acid and heat, and we're going to get back our carboxylic acid and this alcohol. Let's do one more. Acid hydrolysis. Let's take...
Would it still be possible to change?
This would then change to so this is, let's name this one real quick. So this is, we had over here isopropyl butanoic. So here, isopropyl butanoate. So this becomes butanoic acid, that's our carboxylic acid, and we're going to have isopropyl alcohol. I'll kind of put in parentheses here that this is also 2-propanol. Right? isopropyl alcohol, butanoic acid, but we get alcohol and our carboxylic acid. We're going to add some water to this one. Again, we're going to add some heat. We're going to use acid. Let's use some sulfuric acid. Always the same bond. We're going to break these apart. And all I do is simply just draw it separately because they're now broken apart. Chris, what should I bond over here to this oxygen? Right, our two products. If we take carboxylic acid and an alcohol, we make the ester, and if we reverse it, we get alcohol plus our carboxylic acid. So here, should I put? I'm going to add one of these two things here. I'm going to add this to it, or I'm going to add this to it. Which one do you think we should add to this oxygen here? Hydrogen. Perfect answer. I'll rewrite it this way. Maybe you'll recognize it. All right. So we get the alcohol back. This is methanol. Plus, we're going to get our carboxylic acid. Because this water here is going to split up. Let's remember that this is going to split up. Splitting up this, we're separating them. This portion is going to get bonded here, and this hydrogen is going to get bonded to that oxygen there. But it's always, when we split it up, carboxylic acid and the alcohol. Carboxylic acid plus our alcohol. Always that way. Acid hydrolysis of an ester. All right, acid hydrolysis of an ester. Okay. Questions on that before we move on to the last reaction of esters? Not the last reaction of the day, just the last reaction of esters. What two components do you need to make an ester? Carboxylic acid and alcohol. And for acid hydrolysis of an ester, what are we going to get as our products? Carboxylic acid and an ester, and an alcohol, right? Carboxylic acid and an alcohol. So if we can do acid hydrolysis, we can also do base hydrolysis of an ester. Base hydrolysis of an ester. So let's get an ester. A small ester. This is an ester nonetheless, right? This is methyl acetate. Methyl acetate. Base hydrolysis of an ester. Let's see, where are we at? Base hydrolysis of an ester. Let's add potassium hydroxide. So this is our base. Base hydrolysis of an ester. And the hydrolysis is that we're going to break it, right? Lysis, right? To break apart. So we're going to break this apart. And the way we're going to, so this should look familiar, right? It should look familiar. It's always the same bond that we're going to break apart. And we're going to separate these two. So this looks similar to something that we saw earlier today, right? I'm going to separate those two first. So we're going to get this, this, and this. Plus, we're going to get base hydrolysis of an ester. When we remove this, this is going to become negative, this is going to become positive. Okay. So, nope. Ah, wait, what did I do? Base hydrolysis. This. Same bond is broken in. Let's back up to this here. It's very specific how this happens. I broke the incorrect bond here. Is that the hydrogen's going to come off. So the hydrogen is going to be placed here, negative, positive, and we're going to get this. This is what we call a salt. I forgot to mention that earlier, but we're going to get some salt. Right? Even though it's not sodium, we still call this a salt. Okay? So our salt is going to be potassium acetate and some methanol. So using potassium hydroxide and methyl acetate, we break this apart. We get our alcohol back, but we're not going to get a carboxylic acid. We're going to get this carboxylate salt. Right. Let's do another reaction there. Let's do one or two more here. I think the base hydrolysis is a little bit more difficult, and it's a little familiar as well, but want to make sure. It's just the hydrogen that's removed is a little bit different than what we're normally doing. And I do want to get some practice in with line formula. Let's use sodium hydroxide this time. So we're going to use some sodium hydroxide. We're doing base hydrolysis of an ester here. So this is what we're pulling apart. Let me put that in red. So we're going to remove this hydrogen here, and we're going to break apart. It's always this bond right here. We're going to separate that. So let's just separate it first. We're going to get this, plus we're going to get this. Okay? And just remember, right, this is not a carbon here. This is carbon number 1 here. 1, 2, 3. Right? The hydrogen, we're going to get our alcohol back. So this produces our alcohol. And then we're going to take this, and we're going to mark it here. So we get our carboxylate salt. We're going to have propanol, 1 propanol. And 1, 2, 3, 4, 5. This is going to be sodium pentano-8. Sodium pentano-8. One more. So we have isopropyl benzoate plus some potassium hydroxide. We're going to do base hydrolysis on it. It's always the same bond here. We're going to break this apart. We're going to pull that hydrogen off. Let's rewrite our products without those bonds. So we're going to get this plus we get this. What am I going to add to this oxygen over here, Bryant? Hydrogen. And what am I going to add to this carbon over here, Bryant? Potassium and oxygen. The oxygen goes first, then we have our potassium benzoate, and isopropyl alcohol. All right. Break time. We've definitely under break. We have 2 more functional groups, and we have 2 more reactions, I believe. So we're almost there. We're almost there. Almost done with organic, but let's go ahead and take a break. Let's come back at 9:55? Yeah, let's do 9:55. All right. Let's get back to this. We are now going to introduce nitrogen into these structures. So, the first one that we're going to talk about are what we call amines, amines, however you'd like to pronounce that. And let's talk about, where should I write this? This is ammonia. So we have ammonia. Ammonia is a base. But we can make this an organic structure by simply removing one of these hydrogens, and then it will become what we call an amine. So we can replace all of these hydrogens actually with some kind of carbon branch there. So maybe instead of 1, we put 2. Right? Well, this would be NH2 CH3. We could probably write this as nitrogen. So NH CH3 CH3. And we could also write it as CH3, CH3, CH3. We could also write it in this manner over here. So these are all amine structures, and we're now going to learn how to name these amines. So we consider them to be just branches. Right? Here is our branch. Right? The name of this branch is methyl. So we're just going to write methyl. Probably the most difficult naming system we've had. Okay, we're going to call this methyl amine. I know it's difficult. I know, right? We use the whole name. This probably should have started with this one instead of at the very end, right? But here we finally have this one, and there's no space here. Like with an ether, we space them out, and then at the very end, like we put ether here. But this is absolutely just one word. It is methylamine. Because we have 2 of them now, and they're identical, we could use dimethyl. So here we could write dimethylamine. And because this one has 3, guess what we would call that? Any guesses? Trimethylamine. All right, methylamine, dimethylamine, trimethylamine. Any Breaking Bad fans? They were carrying that barrel. They had to steal it for that tanker. They made this absolutely seem like it was so hard to get, and it's not like anybody could really make. I won't show you how, but It's pretty easy to name. All right. Anyways, this is how we can name them, right? And just like our alcohols, right? Our alcohols have classifications, right? Primary, secondary, tertiary alcohols, and amines are the same way. And amines are absolutely easy to recognize, right? Any guesses? Primary, secondary, tertiary? Primary, right? Because there's only one carbon branch here. So this would be a primary amine, right? Because this has 2 branches. Secondary amine, because this has 3 branches, is that this would be a tertiary amine. So pretty easy to recognize the class, primary, secondary, tertiary. And maybe let's change this up. How about we put different branches on here? How about this one, CH3, we'll make this one CH2, CH3, and then how about, let's do CH, CH3, CH3. So now we have 3 different ones. So it's a tertiary amine here. But what's the name of this branch here? Methyl. And what's the name of this one with 2 carbons? Ethyl. And this special structure here? Isopropyl. Now, in order to name this, what rule do you think we could use in order to name this properly? Alphabetical order, right? We can put these in alphabetical order. Ethyl, isopropyl, methyl, and there is no space here. This is ethyl, isopropyl, methyl, amine. Ethyl, isopropyl, methyl, amine. Oh, here's one. How about this one here? This. Four carbons. What's the name of this branch? Cyclo. This is cyclobutane. This is not cyclobutane. This is butyl. Yes, that's what I'm looking for, right? They all end in YL. So it's not cyclobutane, this is cyclobutyl. Cyclobutyl with a YL, and then this would be cyclopentyl, and this is cyclohexyl. Which one would come first? Butyl. So this is cyclobutyl, cyclohexyl, cyclopentylamine. One ridiculously long word. On the lab exam, if you space this out, I mark it wrong, right? There's no spaces in between this. This is absolutely just one word. Cyclobutyl, cyclohexyl, cyclopentylamine. Okay. So I think, we got a good idea on how to name these and how to identify these. Is that let's talk about their basicity, because they are basic. We're going to stick with ammonia over here. We're going to stick with ammonia. And if we put this base into water, we can ionize it. This is my base. This is going to act as my acid. So that we are going to get. Donate hydrogen. Bases absorb, right? They take in that hydrogen, so we're going to get NH4 plus. And we're going to get OH minus, right? So we get ammonium, right? This is one of your polyatomics, ammonium, right? So ammonia, ammonium, and we're going to get here, because we donated that, is we're going to get some OH. So the same thing can happen with an amine. So if we take some amine, let's go with NH2 CH3. And let's remember what happened here. So this molecule received one hydrogen, right? Proton donor, proton acceptor, so it accepted that hydrogen. So it doesn't matter what this was, is that this base accepted one hydrogen, proton, and we gave it a positive charge. So whatever this amine is, the nitrogen is going to accept a hydrogen proton and collect its positive charge, and we're going to produce hydroxide. So we can say that this is now going to be NH3 plus hydroxide. Okay. So this will work for any, again, it'll work for any amine that we're using here. Let's use one that's, let's see, how about, the nitrogen it's gonna accept what? The hydrogen. So we're gonna write it as NH plus, and we're just gonna add the branches. This branch here, this branch here, this branch here, plus we get some hydroxide, right? So anytime we ionize one of those. Now, we've talked about ionization and neutralization, right? Those are different. Bases neutralize acids. Acids neutralize bases, right? So this is simply just ionization. And now let's talk about neutralization. So if I were to take some basic amine, and let's add some hydrochloric acid. This is my base, this is my acid. Acids neutralize bases, but still acid is a hydrogen proton donor. It's going to donate this particular hydrogen here. So proton donor, proton acceptor. We're going to increase the number of hydrogens by 1. We're going to give it this positive charge. I'm going to write this out of the way real quick. I think it'll look better. So we got this positive charge here. So when this separates here, we get these two items here. And the positive charge is that this nitrogen is now containing some positive charge. Okay? This chloride here is looking for something to bond with. So what happens, it just kind of scoots up right next to it. Right? So we only get one product here, methylamine. We name the cation, then we name the anion. So here we have methylamine, but when we go from methylamine to this positive charge here, this becomes ammonium. So methyl ammonium chloride. All right, methyl ammonium chloride. Oh, let's see. Should we do one more? Yeah, let's just do one more here. Let's take. How about we're gonna put this here. So I'm just kind of using these branches now. But for nitrogen, carbon's required to have 4 bonds. Nitrogen, it's only required. It can have more, but it's just required to have at least 3 bonds there. So 1 bond to hydrogen, then we have a branch here, carbon 1, 2, 3, 1, 2, 3. Remember, this is not a carbon here. This is not carbon, carbon 1, 2, 3. But here we have isopropyl, propyl, amine. Let's add some hydrobromic acid to that. Proton donor, proton acceptor. NH2. And we're just going to put that Br minus right next to that here. I won't have you name these. You might see a reaction, but I won't have you name these types here, but we'll go ahead and name this here. This would be isopropyl, so let's get that down. Isopropyl, propyl, ammonium bromide. All right. And that leads us now to our very last functional group. Crowd goes wild. All right. Very last functional group. We were working with amines, and now we're going to consider what we call amides. Right? I'm going to put amide here. I underlined this D earlier on in the lecture. So what we're looking for is some carbon that has a double bond to an oxygen, but now we're going to have this nitrogen involved here. Right? So it's not just nitrogen, but nitrogen with some double bonded oxygen, or carbonyl here. Carbon number 1, carbon number 2, carbon number 3. Now, these are named differently. They're not as easy as our amines were, but they're still not difficult here. So the alkane structure is propane. We're going to, so for an amide, we're going to drop the E and add the entire word amide. Okay. So we're going to drop this E and add amide. So this is propan amide. And that's how we're going to begin naming all of these amide structures that we see here. So let's use some line formula. Let's put a methyl group on there. So carbon number 1, 2, 3, 4. This happens to be a methyl group. So, Kaylin, help me name this here. All right. First, let's start with the branch. So what would I write in order to describe this branch here? Methyl, but first, what carbon is it on? 3. So we're going to put 3 methyl. And instead of butane, because we know it's an amide here, we're going to drop the E, we're going to add amide, and we're going to get 3 methyl. Perfect. Butane amide. All right, butane amide. How about what's that? Carbon number 1, carbon number 2. What would we name the structure? So here, the rule is we're going to drop the E. Yes, so this is a amide. A amide. Now I want you to think hard here, Melissa. I believe in you. Knowing everything we've learned about how to name common structures, right? Ethyl alcohol, methyl ethyl ketone, right? Acetaldehyde. Okay. Give me the common name for this.
I think it's acetaldehyde.
This is acetamide. So this is our common name, right? So we can't have a common name for that. I don't think we're going to do formide, but formide would have an H here. But no, I think acetamide, and it's good to know that common name for that one there. And you know, we can have branches on there. Let's put one with 2 branches here. I think that'll be a good place to good direction. So let's go line formula. Let's add in. Let's put in. Let's just make it an ethyl. An ethyl here and an ethyl here. All right. So Kayla Bowden, help me name this structure here. I'm gonna let you fly solo a little bit. You give me some direction on how to name this particular structure.
3,3.
Okay, and don't go too fast. Let me make sure I write this down. Okay, so 3,3
Diethyl.
diethyl hexanamide. Perfect, perfect. All right. Now, I need you to stay with me here. We're gonna make the next one a little more complex. It's gonna look similar to this. I'm gonna write it over here. I'm gonna use black to start coming out here. But let's go with this structure here. I'm going to put these back in here. You're gonna walk me through this one, Kayla. Come on, I believe in you. You can do this, right? I'm going to give you one piece of assistance here, right? So let's think about this now. Why did you choose 3,3? There's 2 on carbon number 3. Very simple, right? So there's 2 on carbon number 3. And here we see the same thing. There's 2 on carbon number 3. But there's also 2 where else? On the nitrogen. I want you to treat this as if it were a number. Treat it as if it was a carbon, right? But there's no number there, so we're just going to treat it like a number, right? We put 3,3 because they're on carbon 3, but these are on nitrogen. And again here, remember you said 3,3 because both of them are on carbon number 3. So what do you think we can do with this? And we're going to start with this part here first. What do you think we could write?
Would it be
N, I like it. N, comma, N, and then what would we write?
Diethyl.
Diethyl, and then what would come next?
Hexan. Wait. 3,3.
3,3
Diethyl.
diethyl
Hexanamide.
hexanamide. Now, if I did this, how would we change this? If I had to write this, what would we write, Kayla? 2, 2, 3, 3. So 2, 2, 3, 3, and we would change this to what? Because there's 4, monodi, tetra, perfect. We would change that to tetra. So 2, 2, 3, 3, tetra ethyl hexanamide. And I want you to do the same thing here. What would we write?
Would it be NN33 tetraethyl hexanamide?
There we go, right? Perfect, perfect. All right. So we are able to name these. We can name different branches, but anytime we have a branch on the nitrogen, we want to list that just as N. And if there's 2 on there, we would say, if they're the same, because there is one slight difference here. Let's go with this, and I think Sophia was kind of excited, so I'm gonna have Sophia help me out with this one here. We'll make this methyl, and we'll make this ethyl. All right. So here, still 1, 2, 3, 4, 5, 6. So still hexanamide, but here I have 2 different branches. So we wouldn't necessarily do NN, right? So which one would we write first? The ethyl. So how would I start this then?
So N
N-ethyl,
and then
N-methyl, hexanamide. Perfect. Thank you. Right. So all these rules are really starting to stick. We keep practicing them over and over. We come up with, remember different ideas. Oh, we can do this alphabetical order. We can count this clockwise, counterclockwise. We take the shortest path, and it's able to really just name a whole bunch of these. I'm going to draw 2 structures here. We're not going to necessarily need to name them, but we do need to classify them as primary, secondary, and tertiary. Right? So we're looking at this nitrogen, or this nitrogen still, right? And we always want to base it on the number of carbon that we see bonded to that nitrogen. So here, and this is also carbon, right? Don't forget. How many carbons are bonded to this? 3. So primary, secondary, or tertiary? Tertiary. This is a tertiary amine, right? We can take a look at this. How many carbons are directly bonded to it? 1. So this is a secondary amine, and then this would then be a primary amine, simply because it's just bonded to this one carbon branch over here. So again, primary, secondary, tertiary amines. All right. Now let's get into hydrolysis. Acid and base hydrolysis of amines. So let's do acid hydrolysis first. So acid hydrolysis. We'll use a small. We won't go too big here. So here's my amide. Acid hydrolysis of an amide. Acid hydrolysis of an amide. So when we hydrolyze, this is that we're lysis. We're breaking something off, right? So we're going to break it apart, and we always break this one here. All right, it's always that bond where the carbonyl is at, right? It's the bond we always break. So we break these two apart. So let's just do that first. We're going to break this apart. So we have this, and we have this. Now, when we break this apart, NH2, we're going to split this apart. And we're going to split water apart. So here, actually, let me rewrite this one. So we've mentioned this before. Where if we remove this here, right, is that this is going to become, this carbon that's in here is going to become positively charged. Right? And we have this hydroxide here. So we're going to get a carboxylic acid from this. And it makes sense because this is our base, and we should get some conjugate acid, and this is what we have here, right? So base, and then it's some it's acid over here. And now we have to deal with this. Right? So both of those are going to go here, and it's going to get that plus sign. And lastly, we now have to deal with this chloride, and we're going to get Cl-. So this is acid hydrolysis of an amide. Let's do one more. This time we'll add, how about HBr plus some water. So we're going to separate them first. So we've separated this, and we now have just this here. Okay. Let's go CH. So one thing was we've just separated. All right, let's break this bond here. It's always the bond for the carbonyl, and then whatever's off that carbonyl. So all we've done right now is just separate this. We're going to get H+, we're going to get Br-, we are going to get H+, and we are going to get OH-. So let's deal with this OH- first. Where are we going to put that? Off the carbonyl to get our carboxylic acid. These two hydrogens are going to go here, so we're going to get NH3+, and we're just going to put this bromine. Doesn't really matter. We can put it here, here. You know, as long as we put it next to it with that charge here, we're good. But we get this structure here, right? That was acid hydrolysis. Let me write that because I'm going to do base hydrolysis on the other side. So this was acid hydrolysis of an amide. All right. And now let's do base hydrolysis of an amide. So base hydrolysis of an amide. Similar to what we saw with base hydrolysis of an ester, where we produce salt. So this is also going to produce some salt with this structure. So let's put some similar stuff over here. We're going to put NH2, but this time let's use some potassium hydroxide. So we're going to have base hydrolysis of an amide. So always the same bonds. Break that apart there. Break this hydrogen off here. So we have this, and we have this. Right. The O, we've seen this, we're going to make a salt here. And we're just going to add that other hydrogen that's pulling off over here. You can write it as NH3, you can put a bond to it. Either way you want to write it, it's still going to be the same. It's still going to be ammonia there. So we're going to get ammonia, and then we get some salt here, that this is potassium butanoate. Let's do one more. Yeah, let's do one with a branch. Let's use sodium hydroxide. So we're going to get base hydrolysis here. Let's just separate them first, because this is the bond that we're going to break. So we break that bond. So we broke it, removed it, and then on the other side we're going to get NHCH3. We're going to rip this hydrogen off here. We're going to put oxygen minus Na plus, so we get our salt, sodium butanoate, and we're going to take that other hydrogen and we're just going to add it onto here. Right? You could write it different. Maybe you want to write it like this. Okay. But those are our reactions. That is the last of our reactions there. So this concludes organic chemistry. We have an exam on Tuesday. All right. 7-2. That page is important. Memorize all your. I think all of you, most of all of you, have already memorized all your alkanes. We need to know those three formulas in order to determine alkanes, alkenes, alkynes, and to understand that. Isomers, I would definitely know the definition of a structural isomer, right? I would want to know that definition. Okay? If you look at the practice exam questions for units 7, 8, 9, make sure you pay special attention to those, the reactions that are in there, right? Pay special attention to those reactions, because you're going to see reactions set up that way. Is that I will tell you the name of the reaction, I will give you the reactants. You have to then determine what the product of that reaction is going to be, right? If you see the catalyst in anywhere in any part of the product, do yourself a favor, just cross that answer out. Right? They're very popular answers. I don't know what it is, but students see the catalyst sitting on the reaction arrow and feel that it needs to be part of the product, and it just sits there. We ignore it. Put the catalyst on the reaction arrow, we ignore it. It's not part of the product. Don't put palladium in the product. Don't put manganese. Just right. If it's on the reaction arrow, just leave it there. Right. We're not going to worry about that particular catalyst. So do yourself a favor. You can narrow these choices down by removing obvious wrong answers. Okay. But a lot of memorizing required. Other than that, we're going to get started. Let me explain the lab, and then you guys can take a small break and then start the lab, or you can just jump straight into the lab.